Bonsoir à tous. Merci d'être venus nombreux. Merci à ceux qui nous rejoignent en ligne. Et merci à l'Université de permettre d'organiser cette conférence. C'est un privilège ce soir de recevoir Abigail Fraeman du Jet Propulsion Laboratory. Elle est la co-responsable scientifique du projet Mars Science Laboratory avec Ashwin Vasavada qui devait faire la conférence ce soir mais qui n'a pas pu venir et donc Abby a gentiment accepté de le remplacer. Donc voilà, je fais cette petite introduction en français puis après on basculera en anglais. Je crois que c'est en 2004 avec l'atterrissage d'Opportunity sur Mars que Abby s'est dit qu'elle voulait travailler dans l'espace et elle a fait des études en géologie et en géophysique et puis ensuite une thèse à l'Université de Washington à Saint-Louis dans le Missouri en planétologie, où elle s'est spécialisée dans la spectrométrie infrarouge, qui est une technique qui est très utilisée pour cartographier Mars. Et tout naturellement, donc, elle s'est intéressée à la géologie martienne et à l'ensemble des planètes du système solaire et à leur évolution. En 2016, elle va rejoindre donc, le JPL, le Jet Propulsion Laboratory. Et 3 ans après, elle devient co-responsable de ce projet Mars Science Laboratory, qui a déposé l'astromobile ou le rover Curiosity à la surface de Mars 7 années auparavant et qui depuis explore la surface de Mars et c'est ce qu'elle va vous raconter ce soir. Et en effet, le JPL conçoit, construit et opère les engins spatiaux dans le système solaire. Et donc, Ashwin et Abby font partie des quelques personnes privilégiées qui vont en premier les images qui nous reviennent de ces sondes. Il y a 10 instruments à bord de ce rover, dont 2 franco-américains, Kemcam et Sam. Kemcam qui a été en partie construit ici à l'Université, à l'Institut de recherche en astrophysique et planétologie. Donc voilà, comme vous pouvez le constater, Abby est une actrice absolument majeure de cette aventure. Et elle va vous raconter ces 11 années passionnantes d'exploration de la surface martienne. So, ladies and gentlemen, Abby Fraeman, Mars Science Laboratory Deputy Project Manager, Scientist, sorry, and the floor is yours.
Ah, merci beaucoup. Merci beaucoup. Thank you, everybody, so much for coming tonight. I, as you can tell, am not Ashwin Vasavada, so I'm presenting here on his behalf. I will say he is responsible for all of these slides, so if you like the presentation, Ashwin should get all of the credit, and if you don't like it, I will take all of the blame. But thank you all so much for coming. I am so honored to be here in Toulouse and to have the opportunity to speak with you about 11 years exploring Mars with our Curiosity Mars rover. Coming from you today, all the way from California on the west coast of the United States, where I work and Ashwin works as well at the Jet Propulsion Laboratory. We are one of several different NASA centers that are located all around the United States. You may be familiar with places like the Kennedy Space Center that's located in Florida. That's where all of the rocket launches go off. There's the Johnson Space Center in Houston where all of the astronauts are taken care of. Maybe you've heard the famous phrase, Houston, we've had a problem. Over in JPL on the West Coast, we specialize in something different than those NASA centers. We specialize in robotic exploration of the solar system. And so no humans, no rockets, but robot explorers, satellites, landers, and of course, rovers. And we use this to answer all kinds of different science topics related to Earth science, related to astrophysics, and of course, probably most famously, related to planetary science. So of course, I'm here today to talk to you about this wonderful rover that we built, which is named the Curiosity rover. This is actually a picture that Curiosity took of herself on Mars. This is a Martian selfie. We have a camera that's at the end of a robotic arm on Curiosity. That's kind of like a geologist's hand lens. We usually use it to look up close of textures of rocks and soils. But what we can also do is turn the camera around and take pictures of ourselves on the surface and then stitch them all together to make this mosaic. So this is what Curiosity looked like on Mars on the 84th day of the mission. On Mars, we don't call it a day, we call it a sol. So this is sol 84. But of course, the title of the talk is 11 years on Mars. So this is what a selfie looks like about 9-10 years later on Sol 3303. And you can start to see the signs of wear on the surface of Mars. Let's see if I can get this working here. You can sort of see there's all of this dust and even big sand particles that have accumulated on the deck of the rover. You can see there's some kind of holes that are getting punched in the wheels here. But despite looking a little dustier and a little bit more worn for wear, I think it's amazing that Curiosity is still operating beautifully. Her science instruments are still working, and we still have so much that we're exploring and big questions that we're answering even 11 years later. Curiosity and a lot of the robotic exploration that we send out into our solar system, I think, are trying to answer one of the biggest questions that we can ask as humans, which is, are we alone? Are we alone in the universe? And one of the ways that we can try to answer this question is to look at our next door neighbor, Mars, just one planet over, and try to answer the question, is there any evidence that life originated on Mars? If we ever find the answer is yes, if we find there is evidence of life on Mars, that would be huge, because that would tell us that life originated in two places independently in our own solar system. And if you multiply that by thousands and thousands of planets that we've now discovered around other solar systems, the odds that there's life elsewhere in the universe just become incredible. Now, it turns out answering the question, was there life on Mars, is actually a pretty complicated and challenging question. And so our exploration strategy of Mars for the last 20 years or so has been to break this question down into easier to answer bits to try to build up to answering this big question. So the first part of this is asking, did Mars ever have liquid water? As far as we know, all life on Earth requires at least one key ingredient, and that's water. And it turns out that this is a pretty straightforward question to answer using the tools of a geologist. We've answered that question. It's a definitive yes. Mars had liquid water on its surface billions of years ago, and so it now came time to ask the next big question, which is, did Mars have conditions capable of supporting life? And this is the key question that Curiosity has been sent to answer. Now, before I talk about how we're doing that, let me just explain this question a little bit more. What does it mean? What's the difference between just looking for water versus looking for all the conditions you need for life? And it turns out there's kind of three major ingredients that any habitable environment needs. Here's a picture of a habitable environment on Earth. It might not look particularly habitable, but it is, and it might be similar to some of the earlier environments that were on Mars. First thing that you need is not only water, but water that would have been around for, we think, a pretty long period of time, long-lived water. The second thing that you would need would be the key chemical elements and the nutrients that life needs. So this includes things like organic molecules, which are molecules that contain carbon, or things like elements that are really essential to life, things like phosphorus and nitrogen, sulfur and oxygen. Another thing that you'd want to look for are sources of energy that could sustain life. On Earth, we know one big source of energy is the sun that can power things like photosynthesis. It turns out you can also get sources of energy if you have the right mix of ingredients and rocks. And so we're looking for those sorts of clues, those sorts of past environments, to understand, did Mars have all three of these ingredients that were needed for habitable environments? Now, in order to do this, we had to build a pretty big rover to carry all of the instruments that we need. This is what we call the rover family portrait. It kind of shows the evolution of NASA's Mars rovers. Starting here with the Sojourner rover at the bottom, it's about the size of a microwave. And the purpose of this rover was simply to show, is it even possible to get something on the surface of another planet and drive it around? And thank goodness the answer was yes, because then that led to our next slightly bigger rover. These were a pair of rovers called Spirit and Opportunity that landed on Mars in 2004, and they were designed to answer that first question: did Mars ever have liquid water? They were really rover geologists. But to get to this bigger question, did Mars ever have habitable environments, we had to build Curiosity, which is bigger, which is beefier, and it's actually serving as not only a geologist, but also a chemist, a laboratory chemist inside of the rover. Curiosity itself, she's equipped with 10 scientific instruments, including kind of some of these big capabilities that drove the bigger rover. Was a drill that's on the end of Curiosity's robotic arm that can drill into rocks and get this powder that we can then deliver to these onboard laboratories inside of Curiosity that can tell you what the rocks are made of, what minerals are there, and then also search for these very difficult to find organic molecules. Another very important instrument on Curiosity, I of course have to point out, is the ChemCam, the chemistry camera, which is this laser on the top of Curiosity's head. And as Olivier already mentioned, ChemCam was built here in Toulouse, which is so exciting and why we're so excited to be here. So the rover's head is French. Once we built this wonderful rover, we had to figure out where on Mars to go. What site could we land in that would give us the best chance of discovering whether there were habitable environments? And to do that, we looked all over the planet. We used data that we have from our orbiting spacecraft to look at the texture of the surface, the composition of the surface, and we ended up at this site called Gale Crater. This is basically a big hole in the ground that was made when a meteorite smashed into the surface of the planet billions of years ago. And what's really exciting and what drew us to Gale Crater is the fact that in its center is this mountain of material that's almost 5 kilometers tall that we're calling Mount Sharp. And from orbit, we can see that Mount Sharp has all of these different layers of rock. And each of the layer has a different texture. We can see the compositions change. And this tells us that this is a really great place to land to be able to read the rock record. These are sedimentary rocks that were either emplaced by wind or by water, and they record the environment that was around at the time they were emplaced. So it's basically a strip chart in Martian history. Another key thing about Gale Crater is the fact that we could guess about how old it was, and we could tell that it formed right in this period of time, about 3.5 billion years ago, where we think the environment of Mars was actually changing very dramatically. It was going from this probably wet, maybe even warm place to this cold and dry, barren desert that it is today. And so we had not only this wonderful landing site, this strip chart of Martian history, but it also recorded this very critical time period in Mars's history where the planet was undergoing these huge dramatic climatic changes. And so we'd be able to study exactly what happened when that occurred and understand how that might affect Mars as a place that was either habitable or not. This is one of my favorite images that Curiosity has ever sent. And this, of course, is one of the first color images we got after landing on the surface of Mars. We landed in the plains of Gale Crater. We couldn't land on the mountain itself because it was too steep. So we landed where it was really nice and flat on the plains next to Mount Sharp. Curiosity was landed through this amazing system called the Sky Crane. The rover was so big and heavy, the engineers had to invent a whole new way to land Curiosity. So it was basically descended on a cable from this jetpack that was firing off everywhere, and then we had to cut the cables and then have the jetpack fly away, and so it didn't crash onto the rover. And you can see these are, we called them the scour marks on the surface. It's actually showing the plumes of the Sky Crane as it landed Curiosity. So this was such an exciting night. But you know, in addition to this picture showing this wonderful, successful landing on Mars, the other thing it does is if you zoom way in from this kind of telephoto we took with Curiosity's camera to Mount Sharp off in the distance, you can actually see that the rocks that make up the mountain are layers. So just like we predicted from orbit, we were able to see from the ground, and we were able to start to see all of these different units that we predicted were going to be present from orbit on the ground, which was very exciting. So you see these are the cratered plains that were the floor of Gale Crater in the near field of Curiosity. You can see this Martian sand, this dune field that we had to navigate around. Moving up, there was a unit that was associated with a mineral called hematite, which is an iron oxide that often forms in water. Above that, we had what we called the clay-bearing unit. And then above that, we have a unit that is filled with salts. They're called sulfates. You might be familiar with them. Things like an Epsom salt is a kind of sulfate. And in particular, we were really excited to investigate this transition from rocks that were dominantly clay-bearing that may represent a wet environment to these salty rocks that may tell us what Mars was like as it was drying up. So let's go on Curiosity's journey and talk a little bit about what we found over the past 11 years. This is a map kind of showing what Curiosity's done so far. This white line is the rover's traverse. And I'll start at the beginning where we landed at our landing site called Bradbury Landing. We knew to climb the mountain, we'd have to navigate around this big sand dune field. The rover wasn't able to drive through the sand dunes. But the first thing we did was actually, instead of going straight for the mountain, we turned around and we drove in the complete wrong direction to this location called Yellowknife Bay. And we did that because we could tell from the data from orbit that there was a chance that this location was once the site of an ancient lake. And we figured we're so close. We have to just go check it out before we go head to this mountain. So we did that, and our efforts were rewarded. And this is what Yellowknife Bay looked like on the ground. Here's a picture of Curiosity's arm outstretched and touching an instrument. I think probably the alpha particle X-ray spectrometer is what it's called, measuring the composition of the surface. And what we found when we investigated Yellowknife Bay with ChemCam and APXS and the other instruments and drilled into it was that it was exactly what you'd expect for an ancient lake. It had the right geologic structures that you would expect for an ancient lake. It had the right minerals that would form in fresh water. And really excitingly, it contained organic molecules, these carbon-containing molecules that we know are essential as a building block of life. So right off the bat, as soon as Curiosity landed, it was amazing. We could check off one of these major mission goals that we had identified a habitable environment, that Mars, we knew, now had everything that you would have needed to support life. But we were just getting started. We had a lot more to discover. After we finished up at Yellowknife Bay, we turned around and we did make this beeline for Mount Sharp. We had to navigate around this big dune field, as I said. We traversed this as quickly as possible. It still took us about 2 years after landing to get to the surface, the base of the mountain, just because it takes a long time to drive places on Mars. But along the way, we still did some great science. I'll say one of the biggest discoveries that we made during that portion of the mission was finding these tilted blocks of sandstone. So these are slightly coarser grained rocks that you might not expect to find in a lake, but you might expect to find in a faster moving body of water. Or in particular, we could tell by looking at these rocks, by looking at the way that they were tilted and thinking about their relationship with the mountain, that these actually look like the kind of deposits that you get at the front of deltas, which are these features that form when you have rivers that are emptying into lakes. So this is starting to give us a clue about the lakes that may have been present, and that there may have been lakes present that also helped build Mount Sharp. And when we got to Mount Sharp, that is exactly what we found. Here is an example of one of the most, amazing rocks that we found that is pretty representative of what made up the base of this mountain. It's these very fine-grained rocks. You can look up them as close as possible with the hand-lens imager that we had, and it's very, very hard to resolve the grains. They're so small. And you can see also it just has an uncountable number of these layers that are very, very thin, and they're all very parallel to each other. So this kind of a rock is something that's deposited in a very calm environment, something where you don't have a lot of energy moving water around. And this is all consistent with a lake deposit. So we're finding even more evidence of lakes when we get to Mount Sharp. And what is totally incredible is that we saw rocks that look like this for hundreds and hundreds and hundreds of meters of section. So we just kept climbing up the mountain and we just kept seeing rocks that look like this. And so if you think about what that might mean in terms of time scale, we don't know exactly how long it was between the time that every one of these layers was deposited, but if you imagine maybe once a year or so, this is telling you that the lake was around for probably millions, if not tens of millions of years. So Mars not only had habitable environments in the past, but they lasted a really long time. So this is another excellent piece of evidence when you're trying to understand, did Mars have everything you would need to form life? Now, one of the other things we found is that there were lakes, although they weren't around persistently all the time. So we did find these rare occasional intervals where we had evidence that the lake may have dried up for a little bit before forming again. Here's one of the best examples of one of those environments. These might look familiar to you if you've ever been in an area that is usually dry and it gets wet and dry again, like a playa or something. These are actually mud cracks. These form when you have clays that absorb water, and then when the water goes away, they contract and they form these very distinctive geometric shapes in the rock that we can measure and we can look at to understand that this is actually indicative of a drying environment. So this was an unexpected discovery after seeing so many lakes, and the lakes returned after this, but this tells us that Mars was still a dynamic climate even billions of years ago. The other thing we found that I think was a surprising and significant finding are these kind of weird features that you can see cutting up all through here. These strange looking things are actually fractures that formed in the rock that then had water that flowed through them and then left behind minerals that filled them. And then the rock would erode away slowly and then leave these bright toned mineralized fractures behind. These must have formed long after the lakes disappeared, just looking at how they're distributed and how they cross-cut different sections. And so this was also a significant finding because these tell you water had to have been present. Water was probably present in the ground. And so these environments that could have supported life would have persisted for a long time as groundwater as well. So this is something that we saw all throughout Lower Mount Sharp. And it's telling us the story of groundwater on Mars that was pretty new and unexpected, and I think has been another one of the really significant things that we've found and have discovered. In addition to the landing image, this is another one of my favorite images of Mars. This is our drill mosaic. This is just a collection showing 36 of our now 39 different places that we've drilled on Mars and collect samples. I think the most amazing thing to take away from this image is just the different colors of everything. We talk about Mars as being the red planet, but it turns out Mars is really only red because it's covered by this layer of red oxidized dust. And when you blow that away and you get below the surface, Mars is actually the gray planet or the purple planet or the maroon planet. All of these different colors, and all the colors are just indicators of the different compositions of these rocks that formed as environments on Mars changed. And I have to just, brag a little bit, or if you're really interested in what's going on, this is what we did literally last week. We drilled our 39th time. This is a video of what it looked like as Curiosity was drilling into the rock. And here's the image that just came down showing our latest drill hole. So right now on Mars, Curiosity is sitting and analyzing the sample from this hole with our scientific instruments and telling us even more about the story of Mars's evolution and how everything has changed over the planet's very dynamic history. And I think this brings us to the part of the journey where we are today. We landed in the plains, we climbed up all of this lake deposits at the base of the mountain, and so now we're into this very interesting region where we see the transition between these clay-bearing rocks and these saltier rocks. And so the idea is we may be getting to the point that's recorded in this strip chart of Martian history that shows us what Mars was like as the planet dried up. And so this is what the transition looks like on the ground. There's quite a distinctive difference in the way the rocks look. So we saw it from orbit and we can see it from the ground. This clay-bearing unit, it looks a lot like lake sediments, these kind of clayey, flat rocks. But then you move into this salty unit, the sulfate-bearing unit, and instead you're forming these really strange-looking rounded hills with lots of bigger layers. And I'll also take a minute to pause. Wanted to label this feature specifically. You might recognize the name looks pretty French, Montmarcou, and tell you a little bit about, I think, one of the fun things we get to do when we operate the rover, which is name things. When we are investigating thousands of rocks over a decade, it gets really tiresome to say, that rock, no, this rock, no, the pointed rock, that one. It's very difficult to keep track of all of that. So instead, we informally assign names to every single rock we investigate, so it makes it easy to know what we're talking about. And a convention on this mission is that we've decided to name different regions that we've explored after places on Earth that had geological features of interest. So in this particular area, all of the rocks, the theme that we were using was Nontron, which is a town in France, and it is the type locality for a mineral called nontronite, which is actually just like the clay that we had been discovering on Mars. So if you look at the rock targets around this point of the mission, you'll probably recognize a lot of the names as places probably a lot of you have visited. So it was fun for us on the team because we got to learn a lot about France. But when we got to the sulfate unit, one of the first things we saw was that the rocks started to look something like this. So in comparison to those really flat parallel layers that I showed earlier that were really characteristic of the lake deposits, all of a sudden we started to see these beautiful swoopy layers coming in and out. And so these aren't flat anymore. These sorts of curvy layers are exactly what you would expect when you have sediment that's lain down by wind and not by water. So this is one clue that Mars may have been drying up. The water availability is going down, and so instead you have a lot more wind-blown sands moving across the surface. But then we got to this very interesting place that we called the marker band. This is an orbital view. It's kind of just zoomed into this last part of the mission here. So to orient you, here's the clay-bearing unit we drove through. This gray line is the route that Curiosity has been taking. And you can kind of see that there's this kind of darkish, very distinctive layer on the mountain that's really popping out in orbit. And it turns out you can trace this layer basically almost all the way around Mount Sharp. So we called it the marker band. It was something that we could use to correlate different sections and different parts of the mountain. And this is what the marker band looked like on the surface. It's really weird. When we drove up to it, we thought, man, this is really weird. We kind of scratched our heads, perplexed about what it was. It almost looks like a kind of a lava flow you might find called Pahoehoe, but it's not. It makes no sense to have a volcano kind of this high on this mountain. But when we kind of were able to look at it and drive around and look at different places on this very unique layer, and we got on top of it, this is what it looks like. And these are actually something called symmetric wave ripples. So this is a feature that forms when you have shallow water that is kind of sloshing back and forth. So you can imagine something like waves on the shore of a beach, for example. And it turns out, after having gone through hundreds of meters of lake section and not really seeing anything that was very indicative of this, and then going through a bunch of rock that was dry, all of a sudden now, 10 years into the mission, we found the best examples of wave ripples we'd ever seen and the strongest evidence for a lake on Mars that we'd ever seen. So this was pretty unexpected and exciting. And what it's telling us is that this idea of Mars just drying up, it's a more complicated story. It didn't just go from wet to dry and all the water was lost all of a sudden. It's probably this more transient thing. You had a wet Mars and then a little bit dry for a bit, and then it got wet again, but just a little bit wet, and then dry again. And so we're starting to explore all of the details of this very rich transition with Curiosity, understanding both what it means for the planet and then also understanding what it means about the potential for life on the planet. So I think one of the big punchlines of Curiosity, when you want to ask the question, was Mars ever habitable? The answer is yes, for sure. We have now found abundant evidence in all different kinds of geologic settings that were from different time periods in Mars's history, that Mars was habitable. It had everything we needed for life, kind of like all the ingredients to bake the croissant we're out on the counter, and then we're just now trying to ask the question, okay, this is the next step. Did someone put them all together, and did we get that croissant to eat, or are we still just left with flour and butter and sugar? And so we're continuing to explore Mars, trying to answer these questions. But curiosity continues to explore, telling us more about the evolution of these environments and more about Mars as it went through time. I'm going to wrap up, I think, by talking just a little bit about some of the other science that we're doing today, and that's kind of related. And I'll do that. This is one of the areas that we just finished investigating. This is called Geddes Vallis. Geddes Vallis is this big channel that actually cuts down through a big portion of Mount Sharp. In fact, I bet if I go back a couple slides here it is, you can see there's this huge channel that cuts all the way down for kilometers across the top of this mountain. And within the channel, we can see that there's this kind of sinuous feature, this wavy feature that forms this ridge. And so the idea is that this might actually have been one of the last periods of time that there was water on Mars. This may have been an ancient debris flow, which is kind of a feature that you get when you have this slurry of mud and rock and a little bit of water. And it would have brought down a lot of material from higher up on Mount Sharp, and also would have represented one of these last kind of gasps of water ever in this particular area. And so we were able to drive up to this ridge that's right at the base of this channel. And just for scale, I hope you remember how big Curiosity was. You know, it's taller than I am. Here's a simulation of Curiosity as it was parked against this ridge. So this is this huge ridge of material that we drove up close to investigate. And on the surface, this is what it looked like. Geddes Vallis Ridge was covered in all of these different dark-colored blocks. They had all sorts of different textures. We had smooth blocks, we had pitted, rough blocks, and we were able to get up close to them, look at their textures really up close, look at their chemistry, and you know, it's potentially giving us the first taste of what the units are like higher on the mountain, and what Mars was like kind of at the latest period of time that is recorded here. We can also study the different structures that are exposed here to understand just how much water or not was involved in the creation of this feature. Another one of my favorite things that Curiosity has done is we investigated these big sand dunes. So one of the first things you'll notice about the sand is that it is black. It's not white colored like the kinds of sands that you're used to seeing on Earth. And that's because sand on Mars is actually made up of crushed bits of volcanic rock. So this is crushed bits of lava flows. It's similar to a black sand beach you might find here on Earth. If you've ever been to a place like Iceland or to Hawaii, they have them. But what's really remarkable is not the kind of or the color of the sand here. It's actually the structures that you can see in the sand. And it turns out that there are these kind of small scale ripples you can see sitting on top. That's very similar to the kind of structures you get on Earth. But there's also these much larger scale, bigger ripples that are superposed here. And it turns out that ripples of this size and this scale, they don't form on Earth. This is not something that can form in our atmosphere. This is a uniquely Martian process that can only happen because of the very special atmosphere of Mars today, because of how thin it is and its different interactions with the sand. So, you know, it's an interesting science result. It helps us interpret some of the structures that we see in the rock record on Mars. And I think what this picture also really shows us is that, you know, there's a lot of things on Mars that look really familiar, the kind of sand parts of it, but there's also things on it that are uniquely Martian. You would never be able to take a picture like this on Earth. This is unique and only something you could find on Mars. Some of the other fun things that we've done as we've been driving around is we've also been able to find some other visitors from outer space. And in particular, you might take a look at this and say, that kind of looks like a meteorite. And that's what we thought. And it turns out when we look at it with instruments like ChemCam, we find it has the composition exactly like you would expect as a meteorite. So this is actually one of many that we found along the traverse. This is one of the bigger ones. It's the size of a football, or for Americans in the audience, a soccer ball. probably wouldn't want to kick it around because it's mostly made of iron and nickel, so it's very, very heavy. But it's interesting to examine things like this on the surface of Mars because it helps us both kind of understand this process of impact cratering that is ubiquitous across the solar system. It helps us understand a little bit about the evolution of Mars's atmosphere itself because we can look at how these meteorites are weathered on Mars compared to Earth. So even space debris is able to tell us some science. Curiosity also has a weather station. We're constantly monitoring the atmosphere around the landing site, and this is both because it's just scientifically interesting, but also thinking ahead to the future. If we ever want to send humans to Mars, we're going to need to understand how the weather operates in order to keep our astronauts on the surface safe. And this is one of the very dramatic weather phenomenon that Curiosity has observed. This is something called a dust devil. It's when you get a pressure differential in the atmosphere that can actually lift dust and forms. It almost looks like a mini tornado, although it's not like a tornado. You wouldn't get blown away if you walked here. This particular dust devil is very dramatic. We estimated it was about 5 meters wide and probably at least 50 meters tall, although it gets cut off at the top of the picture, so we can't really say how tall it is anyway. But just a really cool example of how Mars today continues to be a very dynamic planet with things that are still able to observe changing and moving. Here's another, I think, one of the cool findings that we found, unexpected findings with Curiosity, and that's this feature called noctilucent and iridescent clouds. What does that mean? Noctilucent, this means it's a cloud that comes out at night just as the sun set, and as the sun sets, what it does is it illuminates this cloud, it lights it up, and so that's what it looks like. Iridescent just basically means it's wispy enough that it forms these beautiful pearly colors. It might be a little bit hard to see in the projection screen here, but if you look at the original image, you can see it looks almost like a mother of pearl. Finding this cloud was really cool. This is something that we didn't know existed on Mars, and we were just kind of staying up late one evening, taking some pictures as the sun was setting right in the early part of winter, and all of a sudden we saw this show up in one of the images, and everyone was like, oh, what is this? This looks really cool. And we didn't quite get our act together to figure out what's going on, but the next time around, and 2 years later, when it was early Martian winter again, we were ready and we took a whole bunch of dedicated observations searching for these features, and we were able to get these spectacular images like this. And so we're learning a lot about Mars. I can also say that looking at the colors of the clouds like this can actually tell you information about the particle sizes that are making it up. So if you're interested in cloud formation on Mars, we have the data for you. So I'll just wrap it up with a recent picture we took looking back. This one we just took a couple of months ago. It's kind of this psychedelic, artisty rendition of Gale Crater. It's actually a picture that was taken with the black and white camera on the rover, and one picture was taken in the morning, and one picture was taken in the evening, and we colored one of those images orange and one of them blue, and we put them together, and we get this, we're calling it a postcard from Mars, and so it's just a really pretty thing to look at, and it was also taken during one of the periods of year where Mars's atmosphere was exceptionally clear. There's not a lot of dust in the atmosphere at this time, so you can actually look back and see the rim of the crater. It's like miles and miles away, kilometers and kilometers away. After 11 years, we've now climbed over 760 meters above the floor of the crater where we landed, and so you can see that landing site way down there, and this really shows just the elevation change that I think we've been able to achieve. And then I'll end on, all of these pictures are my favorite picture, another final favorite picture, which is the view ahead. This is taken with our color camera, looking ahead where Curiosity will be driving in the near future, looking up this Geddes Vallis feature, and it's just going to be a spectacular road ahead. The landscape continues to get more and more dramatic, and as we drive through this area, again, going to continue to understand more about how Mars evolved and understand more about the changing habitability of this place. And I just can't wait for the adventure to come. So thank you all so much for coming to the talk today, And we're going to be available to answer some questions, and I will be joined, very fortunate to be joined by Olivier Ganot, who is our co-PI of the ChemCam instrument, and then Katia Garcia, who is the project manager of the mission. And I will, as they come up here, thank you very, very much for your time and your attention.
Thank you very much, Abby. It's really amazing, and I think there will be mic, so please ask questions.
Two mics, one here, ici, là-bas.
Don't be shy. The first one is always the most difficult one.
Hi, good evening. I was just wondering, first of all, thank you for the talk. It was amazing and super inspiring. But I was just wondering if you're looking for other signs of different sorts of water structures, or if lakes is just the main and only option for Mars. Would there be rivers, oceans, and how would that happen with the Mars atmosphere? Like, how would everything flow and work in this environment?
Yeah, for sure. So in one of the pictures I didn't show, we've actually found evidence for rivers as well in Gale craters. So certainly ponds and rivers and streams were something that existed on Mars, as well as lakes. There is a big question out whether there was an ocean on Mars. Turns out if you map the topography of Mars, there are places that would have supported a really large body of water that would have been big enough that we would have called an ocean. We've only sort of seen hints at it from orbit, though. We haven't gotten down on the ground to really get the data to confirm that. So those, I say, remain controversial hypotheses, but very intriguing. A really big question about Mars is how much water did it have? And where did all that water go? You know, did it have oceans worth of water that have now been sucked into the crust, that are now frozen into the poles of the planet, or that have been lost to space through the atmosphere? And so another thing we're trying to do is integrate all of this information we're finding about water on Mars to figure out how much was there globally in the past.
Do you think I could ask another one? No. Yeah, I don't think there's an arm out there. So apart from that, I think the main question is, where do you go from now? As in, you have already answered curiosity's main purpose, right? So my question would be, how do you prove that there was or there wasn't life on Mars? As in, how do you go from the question of it was habitable, there was life, and like how many steps do you take in between?
Well, as Abby said, Curiosity is part of an exploration program. And the next step is another rover built by GPL, which is Perseverance, which landed in 2021. And the question that Perseverance is trying to answer is there any sign of prebiotic activities? So not necessarily life, because as it was said, it's very difficult to prove on site, but do we have more evidences of the chemistry that happens just before life? That's one way to approach the thing. It's very difficult to do on Mars, and so what that mission does is to collect samples to return to Mars. And now the US and Europe are working on a return mission of these samples to Earth by the next decade. So we can analyze these rocks, and students here, you will be in labs that will analyze these rocks in 10 years from now.
We have a question on YouTube about the piloting of the rover. How is it organized every day?
So if I understand the question is, how is it organized, operations organized? So we have planning cycles, and we have subsystem leads work along with science to plan our sequences. Right now, actually, just as of fiscal 24, we reduced our planning cycles to 3 planning cycles, Monday, Wednesday, Friday. Unfortunately, with the budget reduction, we can't support doing more planning cycles. And we work closely with the scientists to understand what they want to do, their objectives for the day, or for the sol, I should say, as well as any engineering activities that need to be conducted during that sol.
If you have seen movies where you see a bunch of scientists in a room trying to guide people on the moon or things like that, so now these people are totally integrated with the engineering team, and that's what we call the science operations, and we can pick targets, we can decide which one is the most interesting to answer the next question, analyze them as soon as the data come down here on Earth, and close that loop. And at GPL, they have people that are really driving the rover. They have the rover planners. They are really making the decision of where to go, how to go there. As Abby said, it's very difficult to move on Mars. There is no road, no gas station. And so it really takes a huge team to make a rover move on Mars.
Yeah, I just have to add, sorry, one more comment on that. You know, we talk about the scientists in the room. There's hundreds of scientists who help decide where to drive Curiosity and what observations to make. Many of them are sitting in this room, so thank you all for coming. And the scientists are all over the world, including some over at JPL, and then a whole operations center here in Kness. One of the interesting challenges that you might not think about is the fact that, you know, right now it's evening here in Toulouse and it's morning on the west coast of the US. And so we start our planning day every morning at 8 a.m. and you unfortunately don't get to start till 5 p.m. and it takes 7 hours every time we put a plan together. So amazing work helping us operate the rover on this very difficult schedule.
Hi, do you plan to send another robot than Opportunity, like a new robot to Mars, or it's planned?
Yeah, so the United States, after Curiosity, landed another rover named Perseverance, which is helping to answer this next question, was there life on Mars? Mm-hmm. China has also landed a rover in the northern part of Mars. But, you know, thinking beyond that, I hope we continue to land things on the surface of Mars. There's so much that we're learning that you can't tell from just the orbiters. And so thinking about all the other places that we need to explore to understand what's going on. And I'll just add one more exciting thought for the future. Along with the Perseverance rover, there's also this tiny little helicopter called Ingenuity, and it's a helicopter on Mars. It has blades that spin so fast and it's so light that it can actually travel in the really thin Martian atmosphere, and the rover might go 100, 200 meters a day. Ingenuity can fly 700 meters in a single flight. And so could we send, instead of rovers now, helicopters to Mars and make them even bigger and carry science instruments and fly even further? And that would be something that I would love to see in the future.
Thank you.
Yeah, many nations worldwide are now looking for Mars. The Japanese soon will land on the moon of Mars, Phobos. Even Europe is planning to land on Mars with ExoMars 2026, 28.
Hello. How much time are you planning with the JPL to go on exploring Mars with Curiosity? Does it have like an expiration date or?
So right now, our limiting factor right now is looking like it's going to be our power, right? But we are very healthy right now, and we're looking to plan and continue to explore Mars for at least another 8 to 10 years. But we'll keep an eye on what the power profile looks like. We are doing all we can to streamline, which I know there was another thing that was mentioned in the ChemChem, is streamlining operations and making things as efficient as possible. with the newest flight software upload, R13, that was conducted this past calendar year. We're looking to take advantage of a lot of things and doing maybe some activities in parallel that's being explored right now to help continue to maximize size return, but in a smaller period of time, because we may not be able to plan as often in the future years.
I have a question about the figure you showed us within the sand. And you told us that it's only observed on Mars and not on Earth. So do you have any idea why it's on Mars and not on Earth?
Yeah, it's because Mars's atmosphere is so thin that when you have the winds that blow the sands around, it can actually create these different structures in the sand. Earth's atmosphere is too thick. You just don't get kind of the flow over the sand grains that you need to make those rippled structures. It's very cool because when we see that in the modern record, we can then use that to understand some of these ancient rocks that are formed from kind of these ancient dunes that have been turned into stone. And if we see similar patterns into them, that tells us not only are they from ancient sand dunes, but the atmosphere must have been pretty thin even by the time that those rocks formed.
Hi, I had a question about the the Mars poles, about the fact that they contain water. Would there be a mission going there? Would it be interesting, especially to have signs of life, looking at the different, like the sediments you said, so in ice? Is that possible, doable?
Yeah, the answer is yes. People have proposed. NASA actually tried to send a mission to the poles in the early 2000s called Mars Polar Lander. It did not succeed. It unfortunately crashed. But an idea to send a mission there in the future is definitely something that people are thinking about. The poles are exciting because we talk about layers and rocks, but you also get layers of ice in the poles, and so they're a kind of a climate record of modern Mars. And so that would be a really fascinating thing to study. One of the cool things about Mars is that its axis wobbles a huge amount. So Earth, we're tilted at 26 degrees, we wobble a bit. Mars, the whole planet almost turns on its side every 20,000 years, and that changes the climate dramatically. And so we could go to the poles to kind of look at how that sort of a record affected the planet. And then there's also ideas about, are there subsurface lakes in the poles? I'm a little skeptical of that idea, but it's something else that people might be interested to study.
And NASA had another mission close to the poles, Phoenix. That was latitude 70, I believe, something like that. So it was not on the ice, but ice was just below. The plume of the lander removed the sand, and we could see the ice below. It's very hard ice because it's very cold. So coring that ice as we do in Antarctica will be very difficult. It will take a huge engine to do it.
So do you have make any research about the life, the non-carbonic life, and why?
Yeah, so I don't do any specific research on that topic. I know there's some exotic forms of life that have been proposed, silicone-based life, for example. But for now, carbon life is what we know, and so it's easier to study and look for what we know, and that's what's really driving us. We're following the carbon after we follow the water on Mars.
And we find organic materials everywhere in the solar system, so carbon-based. The SAM instrument and Curiosity has identified several forms of organic materials, some with sulfur, some more or less complex. It's really a difficult science because these things are very old and has been exposed at the surface for some time. So the they are modified with time, and you have to, by a model, try to reconstruct what they were to really start to think about bricks of life. So it's very difficult to make that link. But that's what we are working on.
Hello. I was wondering, how do you deduce so much about the history, the past of Mars through this observation? Is it just dating features that you can find on Earth and that looks like what we found on Mars? Or is there anything else?
Yeah, so we don't, well, let's see. We have a rough estimate of the ages of things on Mars that are based a lot on the ages of the moon rocks that we have brought back. So it turns out a really rough way to date a planetary surface is by the number of craters. And loosely, when you have more craters on a surface, it means it's older. Less craters, it means it's younger. So you can look at a place like Gale and count all of the little craters that are around it, and that can help you estimate the age. And when we look at terrains on the moon, that we know the craters and we know the ages of the rocks that we've brought back. That's kind of our chronology. This is one of the things that we're really excited to do with the rocks that we bring back from Perseverance, is actually get to date them on Earth to really help understand, how good are our estimates or not. One remarkable thing that Curiosity has also done is it was able to date a few of the rocks that we measured. We used one of the instruments, the SAM instrument, in a way it wasn't totally designed to work in order to pull out the age date. And what we found was that the rocks that kind of form the basement of Gale, all these sediments, we can tell by looking at the isotopes in them that the way they've decayed over time, they're about 4 billion years old, so almost as old as Mars itself. But then there's some later salts that form, these iron-bearing sulfate salts that are actually like 2 billion years old. So that tells you a record of water that was much younger than when the rocks themselves formed.
Yeah, good evening. I've got a question about the recent geological history of Mars. We talk a lot about how Mars is a very old planet compared to the other ones, but has there been any research into far more recent geological activity?
Yeah, this is one of actually the big discoveries, I'd say, over the last 10, 15 years, is how dynamic modern Mars is today. So I showed you the dust devils that we saw. We've actually seen evidence that the sand dunes are blowing across the surface of Mars today. We have seen landslides that have formed, fresh landslides. One of these features we see are these dark streaks that form in very steep crater walls that are facing the sunny side in summer months. And there's a big debate about whether that means there's actually very salty liquid water there today that forms these darkening streaks. We've also seen fresh impact craters form on the surface of Mars. So, by Earth standards, there's not a lot going on, but compared to our standards that nothing was happening on Mars, we've actually learned that it's quite dynamic. So that's definitely an area that people are interested in researching.
Another question asked by Nabil on YouTube. How deep did you dig into the ground in order to look for traces of water?
Yeah, so there's multiple things that you can look at to put the story together if there was liquid water. The first you can do is just look at the texture of the rock, take a picture of it. And in sedimentary rocks in particular, you can look at the size of the grains in the structures to tell you if they were deposited in a wet or a dry environment. Then we have Curiosity's drill that we use to drill into the rocks, and then we could look at their composition and see things like, say, for example, clay minerals that we know only form in the presence of water. So it's putting together the chemistry and the mineralogy and the sedimentary structures that paints the whole picture about the kind of environment there was.
And so for the question about depth, we have these different layers that have been studied by Curiosity. So what we call the stratigraphy also give us information how it changes with time and elevation. And if the question was the depth of the drill, it's a few centimeters that Curiosity and Perseverance can achieve. With ExoMars, the plan is to try to go deeper, but we know the rock can be very hard, so it's a big challenge.
You said that there is a river flow and a thing like that. Is there any cave systems or things like a cave you can locate on Mars and yeah?
Yes. Yes, there are caves on Mars. The caves on Mars are something called a lava tube, which is something that forms when you have lava flowing and the outside hardens, but the inside keeps moving, and it kind of forms, it's almost like a straw that's left behind. And then if you have a little collapse of part of the top of that tube, then you can see into it. And so we see, especially, you know, on the flanks of these really big volcanoes that are on Mars, we see these pits that just go all the way down, and so those are those lava tubes, and that's another place that people have talked about exploring. They would be quite interesting.
Didn't GPL try to imagine robots that can go into these holes? And yeah, that's amazing.
Yeah, actually, I got to do some field work. We were thinking about if you had multiple rovers and could they talk to each other inside, and so we set up routers inside of a lava tube out in the desert in the southwest, and it was really fun.
And if humans ever go to Mars, they may have to live in lava tubes or in caves just to be protected from the radiations. There is on Curiosity one instrument that is measuring radiations to prepare human exploration.
Hello. Have you faced some big issue with this rover? Like, I don't know, like getting stuck in the sand or something like that, that have been used to upgrade Perseverance?
Yes. We have gotten stuck in the sand, but that was just once, and we got out in Hidden Valley. I'd say the biggest issue that was fixed for Perseverance was the wheels. So Curiosity's wheels they're about the thickness of 6 aluminum cans, and they're made of aluminum. So they're very light, they're very thin, and they're very easily punctured by rocks. It turns out that Mars was a lot pointier and rockier than we had predicted when we landed, and that mixed with those very thin, very light wheels caused a lot of problems breaking holes in the rocks, breaking holes in the wheels, excuse me. And so for Curiosity, when that happened, we worked to figure out ways to slow the damage. So that involved scientists working to try to find terrain for the rover to drive on that had fewer rocks, so it would be easier on the wheels. It involved work from the engineers who developed new algorithms to actually change the way the stresses were put onto the wheel. So if one was going over a rock, it would relieve some of the stress on that wheel to give it a less chance of being damaged. And then for Perseverance, they totally redesigned the wheels, and they're much thicker, and they, so far, I think, have no holes. So that was a great lesson learned from Curiosity that helped the future rovers.
I have 2 questions, more on the rover itself. The first one, how many years did it take to design, to build all the rover?
Well, so the rover was announced in 2003, I believe, something like that. The instruments were selected in 2004. They were delivered in 2008, and there was an extra time. So the takeoff was in 2011. So it takes about 6-7 years to build a rover and the instrument that goes on it, do all the tests. I think it was slightly faster for Perseverance.
Yeah.
So maybe 5 years. So it's really, people are working really hard. I think the team at GPL is something like more than 1,000 people working on a rover when they build it. And even to build an instrument, it takes 100 people. So they are unique pieces. So it's
Good tour.
Okay, thank you. And so my second question: when you want to move or to change the location of the rover, how much time did it take? I mean, do you cross 10 meters? You have to wait to charge the battery, 10 meters again? How it works?
Yeah, so usually with Curiosity, our drive is limited by where we can see. So because Mars is so far from Earth, it takes 10, 20 minutes for any signal to get there. So we don't drive the rover real time because, I mean, imagine driving a Ferrari and you could only see the road 10 minutes ago. You would never do that. So we plan the whole drive at once. And so on a normal day, we'll only drive as far as we can see, which is maybe 30, 40 meters. We do have autonomous software on board the rover that can drive it further, that can say, you know what, we think the terrain's pretty good. You figure out if it's safe and you go as far as you can and drive where we can't see, and we trust you to be safe. And we do that sometimes, and we can do that to get drives that are 100 meters. Perseverance has even fancier autonomy, has gone like 400 or 500 meters. And in that case, usually it's power that does limit how far you can drive. We have a battery that we use. It is trickled charged by this radioisotope that we have on board, and so we will run down the battery, and then we have to wait for it to recharge again before we can do that the next day. And we monitor all of this very carefully when we put a plan together. We model how much are we discharging the battery, and we make sure we're using it as best we can without damaging it.
Okay, thank you.
Hi, I have a question about tectonism. With all the photos that Curiosity and Perseverance have taken, have you seen any evidence of past tectonics of Mars, which is not linked to meteorite crater or impact?
Yeah, so I mean, we've seen things like faults in rocks. This is probably not the question you were asking, but a little bit of tectonism where you might have dewatering of sediment or something that can cause rocks to shift or compress, or impacts that can fracture things. If you're interested in the question of plate tectonics on Mars, yeah, that is a hot topic. It was something that was proposed maybe 20 or 30 years ago. There was some magnetic data that looked a lot like a seafloor spreading center, where you had these stripes that you get on Earth, where the seafloor is spreading apart. You get kind of these positive and negative stripes that represent the poles of Earth changing. And we thought we saw something like that on Mars. And so someone wondered, is that a spreading center? But when we get higher resolution data, they don't look quite like stripes anymore, and we don't see any clear evidence. So then there was a whole thinking that no, there's no evidence. But I think there's now some intriguing things we're starting to find. One of the things we found with Curiosity was this weird rock on the plains that was like almost a granite, which is a kind of rock that you can form in several ways, but one of the ways you form it is by remelting plates as they subduct. We've also found geophysical data from missions like the InSight lander that tells you that there's actually this whole lower layer of Mars's crust that is much less dense than you would expect from just regular crust. It might be more similar to the density of something like a granite. And so I think the overwhelming evidence is still we haven't seen anything that proves plate tectonics is on Mars, but people are starting to re-ask the question.
Okay, so you talked about noctilucent clouds. Is it acting like we know boreal auroras in Earth?
Yeah, so this would be a different phenomenon. So these are just clouds that come out when the sun sets, and they just light up as the sun goes down. Something like the aurora borealis, that's actually the interaction of the sun with the magnetosphere of the Earth. But we actually think there is an aurora on Mars. This is a discovery from a spacecraft called MAVEN. Made some observations that shows that near the poles of Mars there might be this very faint aurora, which was a pretty cool finding. I don't know a lot more about it, so if someone else is an expert, please speak up.
I have another question. So you talked about tornadoes. So I was wondering if opportunity can be able to resist it, or capable to know where the tornado is and how far is it from opportunity?
Yeah, so we don't know where they're going to be ahead of time. So we do these activities where we just take a ton of pictures in an area where they think they might be. Early in the mission, we weren't seeing any, and then it turned out we were looking in the wrong direction. We were looking in front of us, and they were behind us. So once we figured that out, we saw a lot more. We can figure out how far away they are by looking at how much they move between two pictures. We can look at where they are with respect to the landscape. That tells you how far they are, and then how much they move tells you how fast they're moving.
But they don't develop a force very important. The atmosphere is so thin that there is no risk, or you will barely feel it. With Perseverance, there is a microphone, and they record the impacts of the sound blown by the atmosphere. So that's another way to make measurements of it.
Yeah, I was just wondering how we're dealing with two things, which are, how are we dealing with littering on Mars? Because this isn't the first rover we send there, right? And it's not like a satellite that we can just decommission in orbit. And secondly, how are we making sure that we aren't altering anything by touching it?
Do you want to answer? You want me to? You can answer. All right. Yeah, we're bad about littering. Yeah, everything that we have sent to Mars stays on Mars, and it's not going to rust, it's not going to get buried by sand, it's probably going to outlive every single building you've ever seen. If we had the capability to bring back something as big as Curiosity, I think we'd probably want to bring back rocks and not a rover that we built ourselves. So yeah, there's thoughts if there's ever humans on Mars, maybe they'll turn into a national park or something, the area the rover has explored. That'd be pretty cool. Your second question about how do we make sure we don't alter anything is something that we think about very seriously, and the entire international community thinks about. And it's called planetary protection, and that refers to making sure that we don't inadvertently send any microbes to Mars in any place that they might seed hold, because it would be really upsetting to discover life on Mars, but then find out it was just Earth life that we had left behind. So we try to get our rovers and anything we send very, very clean. We have people whose job it is to make them as clean as we possibly can. The other side of that question is also protecting us from Mars. So when we bring these samples back from Mars, if there is any Martian virus or something horrible in them, we want to make sure that that is totally contained and known, and minimize the risk that that would cause any harm to humans. So there are many, many people working very, very hard on questions like that.
Another YouTube question. Noor is asking, when will this mission end?
Yeah, so we don't know. We're hoping many, many more years. If everything goes well, the limiting factor, as Katja mentioned, will be the power supply. We'll just slowly get less and less power over time. But it's a rover on Mars, and something that we've learned is that every day kind of is a gift. It could be your last. Something could happen. The computer could break. The mechanism could fail catastrophically, and you can't go to Mars to fix it. So we try very hard to take very good care of our rover, and so far so good. So hopefully many, many more years.
I had another question here. Yeah. Here. So the Perseverance and the Curiosity rovers, they didn't land on the same crater. And so for now, do you know if there is a significant difference between the results of the two rovers, like the geological features or something like that, like very different things on both craters?
Well, there are similarities and differences. So the landing sites were chosen with that in mind. So we make progress. We explore different places on Mars. Similarities is Mars is mostly a basaltic planet, so rocks that were formed with magma. So we can find some of that on both places. There are also sedimentary rocks, so we can find also a delta. Abby mentioned evidence of that at Gale, and J0 was chosen for the delta at that place, which also is something that the rover has been exploring. But then there are things that are different, like the J0 was chosen because there are carbonates, which is a type of mineral with carbon, very interesting in terms of formation, with water, when we ask the question of where the water went, where the carbon went in the atmosphere. So we try to answer slightly different questions, so choose sites that are slightly different. But at the end, it's the same planet. It's a terrestrial planet like Earth. So like between Earth and Mars, there are similarities. There is also many differences. And this is, by the way, one of our challenge as a geologist on Mars, is that we come with what we know from Earth, and sometimes we project what we know on Mars, and sometimes Mars reminds us that it's a different planet. And it's a little bit the same thing between Gale and J0. Sometimes what we learn from the past mission, we want to project it to the new place, and we realize that, no, the story is a bit different, and that's what we are learning.
Just a question regarding the interior of Mars. Has Curiosity or even Perseverance or any other rovers had the chance to sample or determine any composition of rocks that come maybe a bit further from the depths of Mars?
You want to take that? That's your mission.
I know. So Curiosity is not doing that study, but we did have a project called Insight. We actually just ended this past December. But it studied the core of Mars, and a lot of that information. I am not a scientist. I'm not Bruce Bannard, so I can't give you all the details. But if Abigail has more details on that science, she can give it to you. But certainly, if you go to mars.nasa.gov, there's a whole slew of information about the findings from Insight regarding the core.
Yeah, no, how InSight studied the interior of Mars was with a seismometer, which was actually built by Conférence as well, like a crazy, crazy sensitive seismometer that can measure changes an atom thick or something. And it'd look at things like impacts and just magmatic events that are still happening in the subsurface of the planet, and that gave them enough information to at least constrain the size of the core and the size of the crust, and also found some unusual activity in the planet that we didn't expect. So Mars is not totally cold and dead. There's still something going on underground that I think we need another mission to go follow up on that.
And early in the mission of Curiosity, we also measured some magmatic rocks, coming from magma that cooled down at the surface of Mars, some of which were quite evolved compared to what we knew before on Mars. So that tells us also a little bit of things happening in the subsurface, not as deep as what InSight was looking at, but also from the interior of Mars.
Question about at the altitude or latitude of Curiosity, is there any evidence of a glacier?
Not yet. We're pretty close to the equator, so it would be pretty surprising to find evidence of glaciers, I think. Although there's some intriguing things we see from orbit that I'm excited to look up close. And maybe there was a glacier this far south at one period of time when the planet's axis was, really tilted, as I talked about earlier. So stay tuned. All right. All right, well, I guess we'll go ahead and wrap it up, but thank you all so much. Those were some excellent questions, and there were so many of them, so that was really fun for me and hopefully for you too. But thank you all again so much for your time, for coming, and keep exploring, and thank you again, and thank you for being such a great host as well.
Thank you, Abby. Thank you, Katia. That's really a privilege to have you here, and I hope this is inspiring for everybody here. Yeah. Thank you.